Okay, now, without further delay, I'm introducing tonight's speaker, Rainer Grimm. Rainer's worked as a software architect, team lead, and instructor for about 20 years. In his spare time, he likes to write articles about C++, Python, and Haskell, but he also likes to speak at conferences. He publishes very often on his blog, Modern C++. Now he's a trainer, giving seminars to Modern C++ and Python. His books, C++ für Programmierer, C++, and C++ Standardbibliothek, and the C++ Standard Library were published by O'Reilly and Leapub. So, Rainer, welcome to MOOC++, and thanks a lot for being part of this experiment.
Thanks, Klaus. Thanks for your words. I'm totally excited and totally curious how this works out. So, as you know, my name is Rainer Grimm, and I will today talk about concepts. Concepts in the way we will get it in C++ 20, which is, of course, this year. And I have also a subtitle, which is called Evolution or Revolution. So what is concept, or what will it become? An evolution in C++ or a revolution? This will be the question I hope to answer in my last slide. Let's get started. This is the outline. A few thoughts about motivation, why we need concepts. Then a little bit of the long history to concepts. Then this is the boring stuff. I just explain how they works. Why is it boring? Because they just work. Then the unification of auto and concepts into a so-called placeholder syntax. Then to something totally sweet, syntactic sugar. And the last chapter is about defining your own concepts. Okay. Before I start, there's a picture here from Heraclite, you know, this old Greek. It just says Pantarei, meaning tomorrow the river will not look the same such as today. This just means I gave this presentation in Milano, in Berlin, each time I had to change it because the implementation of concept changed in the meantime quite often. So let's get started with motivation. Why do we need concepts? We have two extremes in C and of course C++. We have function. Have a look here what I can do. We have function which work on a specific type. Okay. Because of that, we need features such as type conversion, such as narrowing conversion and numeric promotion to work with function which only accepts one type or a combination of types. Have a look here. I have here a function which takes an int. Fine. If I invoke it with a double, the double will become implicitly an int. That is narrowing conversion, loss of data accuracy. Okay, this is of course bad. And if I invoke the same function with a bool, bool will be propagated to an int. It's also bad. Why do we need that conversion? Because we can only define one function. How should I say it? If we don't have overloading, one function could only accept one kind of parameters. This means if I want to take in double, I should call this function need double and so on. Okay, this is bad. Function only taking one argument, and to make this happen, we need type conversions such as narrowing conversion or numeric promotion. What is the solution? The other extreme. In the solution are generic functions. Functions which works on arbitrary types, or to say differently, function templates. Have a look here. I have a function, GCD, which takes some type parameter t. Fine. Okay, what happens now when I invoke GCD with two doubles, such as in the second line? This expression here will fail during the process of template instantiation, and I would get an ugly error message. Also not good. So two extremes, both are from my perspective not so good. And now we have the cure, which is called, you can assume, you can guess it, concepts. Now you can express template parameters requirements as part of the interface. They support overloading of functions and, of course, specialization of class templates. In case something bad happens, they produce drastically improved error messages. Then concepts will be unified with auto. We speak now of constraints and unconstrained placeholders. You can define your own concepts. And of course, concepts are always applicable, meaning you can use them for class templates, function templates, or non-template members of class templates. Okay, this was a kind of motivation, but also a kind of overview. And now I have to stop for a few seconds. Any questions so far, Klaus?
So no questions yet, Rainer. Just proceed.
Yeah, okay. Then we come to a next short chapter, which is called the long history. Okay, my first impression, I know concepts since, I assume, 24, 26, I'm not so sure anymore. They reminded me to Haskell's type classes. You can see here a kind of a type hierarchy of interfaces, or type classes are interfaces for similar types, to say differently. And in particular, you see here, equal to, for a type to support ordering, it has to support equality. And you see there's a kind of a system here inside. And this was the first impression I had when I encountered concepts. Concepts are different, but this was my first impression. I will come to this impression back later. Only to make my point, concepts are different to type classes. Concepts are a compile time story. Concepts, you can use, for example, non-types for concepts. Yeah, and a concept is more a kind of a predicate. So only to say it's different from a type class. But this was my first impression. And a few words about a long way of concepts. In C++ 11, concepts, to put it another way around, concepts should be this big feature in C++ 11, but they were removed. And you can read the reasoning for it. They evolved into a monster of complexity. Okay. Interestingly, they were removed in Frankfurt in Germany. And what I like about this story is that the nice feature of C++ 20, or one of the big features of C++ 20, contracts were also removed in Germany. This time it was Cologne. Seems to be a bad place to making a standardization meeting. Okay, in 2017, they were already removed in a lightweight version, Concept Light, but with 20 we have them. And that is the reason why I want to talk to you. Okay, you see, next time to ask a question. Klaus, I say something?
No, so far, and no questions either.
Okay, now we go to the more interesting stuff. This was more an overview on motivation. Now I called it kind of boring. It's not boring, but it just works. And in this regard, it's boring. Have a look. Boring is, to say differently, a virtue in programming languages, because if something is boring, you immediately understand it. Okay, here is a concept. You see it? Sortable. And I just use it in 3 different ways. In the so-called requires clause, this means that the type parameter cont has to support the concept sortable. You see, requires, it's a requirement. You also can use it as a in the so-called trailing requires clause. Have a look here, requires sortable cont. And the syntax which I most prefer because of readability, just use it instead of type name or class. You see, sortable cont. This means sortable is a concept and it's applied here. And you see, I applied to the function template sort. Okay, let me play with it. This is a command line or an error which I got with an previous implementation of concepts, but this will not change so far with the standardized concepts. So we have here a list. What I want to do is, of course, I want to sort the list of integers. And this will fail with a terrible error message. And what is the reason for the error message? Std sort requires that the container such as list is supports a bidirectional, a random access iterator. A list only supports a bidirectional iterator, and this is the reason why we get this error message, which would be terrible long if I would not use a concept. Terrible means more than one page. Okay, only the first impression. What is a concept? I wrote here a small sentence. A concept is a constant expression, something which can be evaluated at compile time, and it's a predicate, something which returns true or false. This is a concept, a compile time predicate. Okay. Now I show you different use cases of concepts. Only to give you an idea in which context you can apply them. For example, I define here a vector, my vector, taking an object. If I want to instantiate this vector with a reference, you see it ref, I get such as int ref does not satisfy the constraint object because it's not an object, it's a reference. So this works. Let me show you other examples. For example, I can also use it for applied on a member function. And you see here push back. And this requires that T, the elements of the vector, are copyable. If not, I would get a readable error message. Okay, I can apply to classes. I can apply it to member function. What else? This is a little bit more sophisticated. You know, we have functions, variadic templates since I assume C++ 17, and all determines if all arguments evaluates to true, and then of course it returns true. Any determines if any of the arguments returns to true, and then the result is true, and none, of course, determines if none of the arguments returns to true. And here I applied a concept. This is a fold expression, which I called arithmetic. This means I can use it in fold expression, and here I require that the type parameter is something like something arithmetical. Okay, and here at the bottom you see how I use them. I say all on true. Of course, this is true. All on 5 to 5.5 false is false because false is evaluates to false. Okay, so you see I can apply them even on variadic templates. In this case, it's a special case of variadic templates. These are fold expressions because of this expression here. Okay, let's continue. You can apply more than one concept. This looks a little bit scary, but let me explain it to you. I want to find something in a sequence S which should be a sequence container, and the elements should support equality comparable. So I have here I applied here two concepts, one to the container and one to the elements of the container. Okay. And this is maybe the fifth version of Stud Advanced you see. What is Stud Advanced? Stud Advanced is an algorithm of the standard template library. It takes an iterator such as iter and a number n and puts the iterator n position further. Okay. And there's something you have to respect. What do I mean by respect? Depending on the container, you can to put it another way, each container supports a specific iterator. For example, a forward list supports only an input iterator. A list, as we saw before, supports a bidirectional iterator. This is, of course, in concept. And a vector, stud array, stud string, or stud deck supports a random access iterator. And why is this important? If you want to put an iterator 5 position further, it makes a big difference if you say 5 times next, or just makes internally pointer arithmetic, which is of course faster. So depending on the capabilities of the container, a different version of Stud Advanced is chosen. And you as a user just say Stud Advanced, and the compiler use the best fitting version for you. In this case, it's a list, so a bidirectional iterator is chosen. This overload is chosen. But if I would use stud vector of int, this version would be chosen, and this is of course faster. This has constant complexity, and this one has, I assume, linear complexity. Okay. Of course, we can specialize on concept. Here's the primary or general template. It takes all type parameter. You see, type name t. And here is the specialization for object. If I now instantiate my vector for an int is an object, this specialization would be chosen. If I use it with an int ref, this general version would be chosen. So concepts also supports specialization of, in this case, class templates. Okay, you see, now it's time to make a break for me, and I'm not sure if you have any questions so far. Yeah.
So there has been a question whether you're going to show how these concepts are going to be implemented.
This is the part which you have a close look here. This will come in maybe 20 minutes. Right. Define your concepts.
Then next question. You've shown the advanced function. Mm-hmm. And now there's 3 different versions of advanced based on different types of iterators.
Yep.
When C++17 came out, we were given if ConceptsInC. Everybody said we should put everything into one function, and we were proud that we have only one function that deals with all different kinds of iterators. Now we're back to 3 functions.
Maybe, sorry, maybe you're right. My point was only to make this point clear that we can overload on concepts.
Okay, so the question is bad. The question is, did you make a comparison whether this version or perhaps the if ConceptsInC is faster from a compile time point of view, or did you compare the solutions?
Honestly, I didn't compare it, but I assume that they are similar because it's a compile time decision. So what should be the difference? To make the difference, you should look at the assembler code and then Godbolt, and then you should have an idea if there is a difference or not.
Yeah, honestly, that would be runtime performance, wouldn't it?
Sorry?
That would be runtime performance, but okay. No problem.
Now, if you look at the sampler code and the same, it boils down to the same code. So this was my point.
All right. And then the last question was about the specialization from a syntax point of view. Usually in a class specialization, I have to use angular brackets after the class to make it a specialization. Can I now omit these angular brackets? Can I really just say template again without having to provide some special types?
I don't get your. I know it's now about the syntax, but I don't get your question.
So usually,
what should I change here?
After my vector, I have to give a couple of template parameters. I have to use angular brackets to syntactically make this a specialization. Now here it's not. This is the interesting detail. Can I omit the angular brackets in the specialization? Does the compiler realize this is a specialization?
You mean I should omit this object T? And what should I do instead?
So my vector, angular bracket open, something, angular bracket close. This would be the syntax for a class specialization. And now it's not necessary anymore.
Oh, sorry, I don't get it. Can someone kick in and help me? I don't get it.
No problem. We have another question though.
Yeah, sorry.
So,
yeah.
How would the compiler make a decision if two or more types fit? So for example, if the iterator has both bidirectional and random access.
Yeah, okay. The most specialized one will be used, such as with partial and full specialization. And one is more specialized than the other if one can take a subset in mind of the other. This means more specialized.
All right.
Okay.
All the questions. Thank you.
Okay, thanks. One additional remark to this question I can't answer because I was not able to understand. I'm not able to understand it. You can write me an email, and I won't try to answer it, and then we can put it on some platform, and all can read it. Okay. Okay, let's go on. Now I come to the placeholder syntax, and I start with something which was not so nice. You know, I teach C++, and to teach C++, I always look for symmetry. This means all features should behave in a similar way. And we had a big issue with C++ 11 and C++ 14, which is of course solved with C++ 20, because if not, I would not say it to you. But anyway, okay, what is the issue? What is the standard template library from a bird's eye perspective? We have generic containers, generic algorithms, and you can apply a generic algorithm on a generic container. And the glue code is, of course, the iterator. This means you can say std sort on a vector of ints, but also on a deck of strings. Anyway, it works. It's just generic. Sometimes, I want to put it another way, we have std sort. Sometimes you want to sort in vector of strings. Okay, fine. The usual way to sort in vector of strings is lexicographically, meaning such as in a phone book. Okay, you know what that means. But sometimes you want to sort this vector of strings in a different way. For example, reverse, for example, case insensitive, for example, based on the length of the strings. Okay, to support this use case, std sort has an overload which takes an additional predicate, which you can use to provide the sorting criteria. Fine. But now we had a big issue in C++ 11. Why? This is the ideal use case for a lambda function. This means you say std sort, begin n, and then you provide your additional argument how to sort. Fine. But we have generic containers in 11, generic algorithms, and type-based lambdas. This was a break. We have a generic Lego brick system which has a component which is not generic. Okay, they solved this issue. Why? How? You see, with C++14, we got generic lambdas. You see this auto here 2 times. Fine, but there's another issue. What is a generic lambda? A generic lambda is understood a function template. It's just another way to write this stuff conceptually, you see? So what happened in C++14? We introduced a new way to write function template by using type arguments, which are auto type parameters. And you know what happened in my seminars? My participants asked me, why can I not use auto in a function definition? This function definition becomes a function template. Then I said to them, this is an exception of the rule. You can apply auto only in lambda functions. But this is a lie now, because in C++20, this asymmetry is gone. Okay. Now let me talk about placeholders, which is the general term for auto or the auto. Okay. In C++20, we speak of unconstrained placeholders. Have a look here. And constrained placeholders. Unconstrained and constrained placeholders. An unconstrained placeholder is just auto. Fine. A constrained placeholder is a concept, such as integral. And when can you use an constrained placeholder? Quite easy. This is quite easy to get. In each case, you could use an unconstrained placeholder, such as auto. Let me show you a few examples, and then you see it's quite easy to get. Here I define my first concept. Never define this concept. This is part of C++20, but anyway, only to show it to you. So I defined the concept integral, and I use under the hood std_is_integral, which is a function from the type traits library, which determines at compile time if t is integral. So something between bool and long int. Okay, here I use it. You see, the return type of this function getIntegral is integral auto. Not auto, integral auto. It has to return something which behaves such as an integral. Let me continue. I use it here in a for loop, a range-based for loop, integral auto. I can use it to give the for b, to put it short. I can use it for the return value of this function getIntegral. And here only to see, this is of course the 11th syntax. Once more, integral auto is a constrained placeholder. Auto is an unconstrained placeholder. In each place you can use an unconstrained placeholder. You can use with C++20 and constrained placeholder. Constrained placeholder, of course, a concept. Okay, only to show you, this is the output of the program, which is boring, but it works. I have to admit a little bit. I used in this first example not concept, how should I say it? A previous implementation of concepts, so-called ConceptsTS. ConceptsTS stands for Concepts Technical Specification, but the output would be the same. Okay, you see it works, and it gave me the expected results. Okay, before we come to something sweet, any questions so far, Klaus?
So no further questions at this point, Rainer. Please continue.
Okay, fine. Okay, fine. Then we come to something sweet, and this is for me. Oh, I forgot to say it. I'm a totally fan of concepts, but maybe you hear it. Okay, to syntactic sugar. If you say syntactic sugar is not necessary, we don't need syntactic sugar. This is false. Syntactic sugar is totally important. Syntactic sugar only means we cannot do something new, but we can do something old in a nicer way. To make it easy to get, maybe C++ is syntactic sugar for assembler. So, of course, we like syntactic sugar. Okay, now to the syntactic sugar. I want to apply the concept integral, such as before, GCD, greatest common divisor. This is the, here I use the requires clause. This is classical. Sounds strange classical, but it's classical. Then I use it here in the so-called constraint version, constraint type parameter. Instead of type name or class, I say just integral. And now starts the syntactic sugar. Have a close look here. I define GCD2, which takes two type parameters, which are called integral auto AP. And it returns also integral auto. This is under the hood a function template which accepts and returns only arguments which are integral. This is a new way to define a function template. I should not call it, but I will call it in such a way. This is a constraint template because it uses constraint template parameters. And this is also possible in C++20. You can now use also auto, which gives you an unconstrained template. So all types or all values for A and B are possible. This is new, and this is the syntactic sugar. It works. It's a piece of cake now to define a function template. And let me continue here. Okay. This is boring. You see, it worked. I just applied it. I have to make a short detour. Why? With the concept TS, once more, concept TS is the technical specification. This was the original specification of concept, which changed a little bit to the C++20 concepts. In the technical specification, if you specify integral auto A and B, both values A and B had to be of the same type. This restriction is gone with C++20. Now they can have different types, but of course both have to be integral. So, and this is fine. Why? This is exactly the same way auto works, and from symmetrical reasons they should work the same. Once more, A and B in this first case and also in the second case can have different types, but they have to be integral. Okay, in the first case at least. Okay, what we can also do, which looks a little bit special, we can now overload. Have a look. This, once more, is an unconstrained template. This boils down to a template because I use auto as a type parameter or as type specification. This is a constrained template because it uses integral auto, and this is a usual plain old function. It just takes long. When I now invoke it with, have a look here, with a double, with an int, and with a long int, the compiler chooses the right one. This means for a double, the general case is used, or the function template without constraints. For an int, The middle one is used. And for long int, of course, the plain old function. So overloading also works on functions or works, sorry, on concepts. And once more, this is a template, this is a template, and the third one is not a template. Okay. Now to something we don't get. This is the reason why I wrote the headline red. Okay, this was part of the concepts TS, so of the original proposal. And there was a new way to define templates. Have a look here. Instead of template integral T, here I say T should be integral. I could say integral curly braces T in the, I call it template header. Okay. What I didn't like about the syntax was here I could only use integral, but not auto. This would also be an exception of the rule. And I don't like exceptions. I like symmetry. Let me bring it to the point. Here you see, I defined a function template GCD once more, and this time with this template introduction syntax. This is the official name. And here I say this is constrained because T has to be integral. But this syntax would not be possible, auto T, which is crazy for me. But anyway, I don't care because we don't have it in C++20. Because why it's crazy, I can quite easily overcome this restriction by defining a concept which always returns true. Now it would work, and now it is a kind of an unconstrained template. But I applied an ugly trick. Okay, but anyway, I don't care because we don't get it. Okay. Okay, this is just the application of the constraint class. It's not so interesting. You see it worked. And this only works with the concept TS, not the concept which we get with C++20, which I will show you in a few seconds. So now I'm looking for questions.
All right, so the first is a technical comment. Lucas asked me if I could ask you whether you have the stream open. If yes, could you try to close it? Perhaps this gets rid of our sound issues.
What do you mean by stream open?
So the Twitch, do you have the Twitch?
No, I don't have the Twitch open.
Okay, perfect. Then let's continue with the questions. There have been quite a few.
Okay.
So would you go back to the very first slide that you showed with the QCD in the syntactic sugar chapter?
Strange. Wait a second. Now I have to focus back. Okay, syntactic sugar. Here we are. Here we are.
So is this the first slide? This is the first one. All right.
You see, this is the first one, and this is the second one.
Perfect. This is what I mean. So the question is, if you pass a non-integral type to the last example, what error will be thrown?
Do you mean GCD 3?
So I mean I believe, yes.
Yeah, you will get the behavior you get. To be honest, I never tried it out, but I'm relatively sure what would happen. This will be, template instantiation is eager. And this will exactly apply A modulo B, which will not work for example, for a float. So you will get as error message all what happened before. This is the side effect of template instantiation, which we love. All what happened before would appear on the screen, and then you have to look for the error message and get an idea what was going wrong.
All right, then next question. On the left side, GCD and GCD1, you can clearly see that the two parameters have to be the same thing. But on the right, it appears as if they both could be different types.
Perfectly Perfect question. You are totally right. Not you, the man
Yeah.
who or woman who asked the question. Totally right. There's a little bit a lie here inside. You're right. GCD1 and GCD2, GCD and GCD1 requires that there's one type parameter called T, and here they could be different. Yeah, you're right. So the right versions, GCD2 and 3, are a little bit more, of course, they are more powerful.
All right. And is there a way to specify with the abbreviated syntax that both types have to be the same?
Mr. Appropriate, yeah, you can use here, you can use in the second argument tackle type of A instead of integral auto. You know what I mean? You did use the type of A, and this must be the type which B should have. This is a trick. A
Okay,
is
I know what you mean now. Yeah.
A is free. It should be an integral, and you use A. You did use a type, and this type is the type B should have. So tackle type of A should work instead of integral auto.
All right, and the last question. When using the abbreviated version for auto, for normal template functions, can you still use the angle bracket syntax like you will be able to do for lambdas?
What's not? We talk about GCD3, and
can I use the angle brackets like I will be able to use them for lambdas in C++20?
You say you want to use GCD, GCD1, and GCD2, such as here, and then you want to define GCD3 with the classical syntax. I never tried it out, but I assume it. If not, it would be terrible, counterintuitive. I never tried it out, to be honest.
Okay.
Okay.
Right. Thank you.
Was it? Did I answer? Or did I answer all questions so far?
I hope so. Yeah.
Okay. If not, no issue. We have enough time left at the end. Okay, now we come to the, for me, most interesting part is to define your concept. First of all, don't do it. This is only an overview of the concepts we get with C++20. And you see, there's an integral available. There's no reason to define your own concept integral. Let's have a look. We have language-related concepts, same as derived from convertible to, common with, assignable from, swappable. Okay. Then we have arithmetic concept, integral, signed integral, unsigned integral, and floating point. We can compare something, Boolean, equality comparable, totally ordered. We have concept for the lifetime of an object, destructible, constructible, default, move, copy constructible. We have concepts. You will see these concepts in a few minutes. I will use them. We have concepts such as movable, copyable, semi-regular, and regular. Maybe you don't know what that means, but wait a few minutes. I will implement them for you. And of course, we have invocable, regular invocable, and predicate. A predicate is a function which returns true or false. And regular invocable is a kind of pure function, a function which always returns the same result, the same result when given the same arguments. Okay, these are not all concepts. There are more concepts. For example, in the ranges library from Eric Niebler. But anyway, this is only an overview of the most important ones. And now let me continue my story. Here I define a concept, and only to see the difference, this was the original syntax. It was, I call it direct definition. It was a little bit like a function definition. You see, concept, it returns a bool, integral, curly braces open, close, and internally, the concepts often boils down, or most of the time boils down, to a function from the type traits library. I hope you know the type traits library. This is a library consisting of maybe 100 functions, which allow you to ask type properties at compile time. In this case, I ask if t is integral. Okay, and this is the official new syntax. You see, it's a little bit more concise. Concept, but I use the same type trait. Okay. Okay, T first. Okay, this is not so interesting. I was a little bit irritated about my desktop. Anyway, okay, you see, this is the original syntax, and this is the new one. This is the proposed one. You can specify or define more sophisticated concepts, such as here, which looks a little bit more interesting. Here I define the concept equal, and this is the old syntax, and it requires that both arguments are of the same type, t, that two operators equal and non-equal exist, and they return a bool. So in type, which supports equal, has to support this kind of interface here. Okay, this is the original syntax, and this is the one we get with C++20. You see, a little bit more precise, a little bit more concise, sorry. Okay, I have to say I lied here a little bit. You should not write it should return a bool. You should write it returns something which is convertible to a bool, but because of space limitations, I use this shorter form here above. So you should write it in this way. A equal to P should return something which could be convertible, which is convertible to bool. By the way, stud convertible to is a, wait a second, stud convertible to is a, sorry, here, a concept. So this concept uses a concept for its definition. Okay, this was equal. Let's try it out. Here I define a function which takes two arguments which should support equality. You see, equal auto. And here, this is the reason why because I apply the equal operator inside. Here, to make it explicitly, I define two types. One without equal, because I deleted the equal operator, and one without unequal, because I deleted the unequal operator. I put it to delete. You see it here. This is keyword. Okay. Now I apply are equal to 2 ints. And of course, you know, ints can be compared, in particular on equality. But if I use these lines, this should fail, because without equal does not support equality, without unequal does not support inequality. And here's the output of the program. You see, this is a good case, works, but, sorry, it's a little bit small, but when I use this time, wait, one step back, when I use this without equal and without unequal, it fails. And it says exactly why it failed. You see, equality and inequality would be ill-formed. Both is compiled on my Linux desktop with GCC. I only switched the colors a little bit. If not, we could not read the error messages because of color reasons. Okay, and you see here, I used here ConceptsTS, the previous version of concepts. But I will show you in 5 minutes the new error messages, which are totally similar. Okay, this was equal. And now I want to make a comparison, because I was was curious. I was curious if I can implement something similar elegantly, such as type classes in Haskell. Okay. Have a look here. This is the way in Haskell equality is defined, the type class equality. Equal E, and it requires equal in equality. Of course, this will be written a different way in Haskell. And A goes to A, goes to bool, means both parameters have to be the same type. And this is the corresponding syntax in C++. And you see, it looks kind of similar. This time I use std convertible to. Okay, what does equal require? Once more, A and B have to be the same type. The type has to support equal and inequality, and the result has to be convertible to bool. Fine. Why? Now you see why I want to show you Haskell, and then you see why what's my story I want to tell about C++. Once more, this is part of Haskell type classes hierarchy. In particular, a type which supports ordering has to support equality. This is a kind of a dependency. Now I want to build or to model this in C++. Let's have a look. This is the way how Haskell expresses it. You see, to support ordering, A has to support equality and this 6 additional operations. Smaller, smaller equal, bigger, bigger equal. Equal compare max because it's quite easy to implement in C++. But this is my point. In Python, so in Haskell, I can use an existing type class equality and put it as a requirement for an extended type class. And now the question is, can I do something similar in C++? Of course. Have a look here. Here I define the concept ordering. T has to, in case T should support ordering, this means T should support equality and this 4 additional operations or operators. And you see, smaller, smaller equal, bigger, bigger equal. And of course, convertible to bool. And this is for me extremely elegant. I can refine a concept such as could refine a type class. Okay, let me try it out. Once more, the function are equal. We know it from before. And this time, I defined, to be honest, this is a function template, or here I defined additional function template, gets smaller, which requires that A and B support ordering. Why? Because I make here the three-way, apply here the three-way comparison operator. Okay, let me try it out. First, I use it for ints. Of course, ints can be equality compared and can be ordered. This is trivial. But this will not hold for unordered set because it's called unordered. This means I can compare unordered set, can apply the equal operator on unordered set, but I cannot apply ordering on unordered set because they are unordered. Now let me show you the error message. This is, of course, the good case. And this is the case I used unordered set. And here you see exactly what was going wrong. The expression E smaller equal B would be ill-formed and so on. And this is exactly the error message I got with when I invoked this function using a concept. extremely readable error message. Okay. Now I want to talk a little bit about semi-regular and regular. We have often the term in C++, we talk about a value or something which behaves such as an int. This is formally the formal term for this kind of type is a regular type. What does regular means? Regular means a type has to support the big 6, swappable, and equality comparable. Once more, what does big 6 mean? Big 6, once more, default constructor, destructor, copy move assignment. Oh, I cannot count. And copy move constructor, big 6. In addition, if this type supports swappable, we call this type semi-regular. And if it also supports equality, we call it regular. And to make it short, a regular type is a type which behaves such as an int. This is a phrase in C++. And to put it another way around, this kind of types behave very well in the C++ ecosystem. So we want to have regular types. And this is the reason why we have concepts semi-regular and regular. I now implement it by myself. And afterwards, I say to you, it's not necessary because we already have these concepts. This is the way I implemented it. Looks a little bit wordy, but it's quite easy to read. Here I define a new type trait, which I call is semi-regular. And you know, to be semi-regular, you have to support the big 6, default constructible, destructible, copy move constructible, copy move assignable. And in addition is swappable. This is quite easy. And I combine them with a logical OR. So this was extremely easy to define. Now I can use this type trait here in this line. And you see, I can define now the concept semi-regular, which uses this type trait I defined here above. This is my concept semi-regular. And if I use this concept semi-regular here, combine it with equal, I have, of course, regular. Now I defined two concepts, regular and semi-regular. Okay, let me continue. This is the way, once more, this is the way I defined it. But I should not do it, only to show you how you could implement it, because it's already available. This is from the standard. This is the official. See, this is stud semi-regular, stud regular. And this is the way it's defined. First, they define the concept movable, which means is object and is move constructible, assignable from, and swappable. So use under the hood type traits and also concepts such as swappable. Next, they use movable to define the concept copyable. And this is enough to define the concept semi-regular. Of course, you have to add the concept default constructible. And based on that, such as I did it, they defined the concept regular. You see, it's a little bit different, but also kind of similar. Now let me apply this both concepts, my defined concept regular and the concept from the standard. And to use it, I have to include here the header concept, you see? And here I define two functions. This is my function, which uses my concept regular. And this is the function which uses the concept regular from the standard template library. Okay. Now I define a type equality comparable. It's a little bit a short type, but anyway. And I define for this equality comparable the equal operator. You see, this type can be compared using equality. And then I define and type not equality comparable, because this type could not be equality compared. Okay. Now let me apply both functions. First, I do it with an int. Behaves like an int is the function template using my concept regular, and like an int2, the concept using stud regular, such as here above. I do it for an int, I do it for a vector, I do it for equality comparable, and I do it for not equality comparable. And this is the key line, you see, because this line would fail. This is the first time I show you output, at least a part of output from the C++ 20 standard. If you want to try it out, you can use this link. Then this program would run, which I showed you before, and you would get this error message. This error message is extremely verbose, and I only show you the key parts. You see, this is the error I got from my concept regular. This would fail, or is invalid. This is invalid. And this is the message stud regular would give me. You see, kind of similar, and both work the way we say should work. So when you get the presentation, use this link here, and then you can try it out. The newest GCC supports this C++ 20 concepts. Also, you can use quite current Microsoft compiler, but I'm not so happy about the error message. This is what the Microsoft compiler gave me, just no matching overload function found. This is for me too unspecific. This is the error message I would get, or I got, when I used this program, which requires here that the type should be regular or support stud regular. Okay. You see, I'm done with my first overview. Okay, 60 minutes. Before I continue, any questions so far? Klaus, it's your turn.
A couple of questions.
Oh yeah.
Somebody is wondering, what about const? So if you use the integral concept, integral const autoref, would it look like this?
Wait a second, which page was it?
So, I think you did not show it, hence the question. Integral const autoref. If you would like to return something that, so if you would like to return a constant reference, but constrained with a concept, how would it look like?
Oh, this is also something which is too difficult to imagine in my head. We should write at least once more. Once more, Klaus, please.
Okay, so integral const autoref. Would it look like this? So you showed always integral auto.
Okay.
Now somebody wants to know if integral const autoref would be valid syntax.
Interestingly, I never saw it, to be honest. I never thought about it, to be once more honest. At least I understood the question.
All right.
I never saw it. Does it make any sense? I never thought about it, to be honest. I never I studied the stuff in the draft for the C++ 20 standard, so the PDF. And also you can look at a CPP reference. There's quite a good documentation to concepts, but I never saw it, to be honest. If someone could kick in, maybe someone of the listeners, maybe he could use the chat window to give a definitive answer, but I don't have it. I don't know it.
All right, then let's continue with the next question. So I just read it. When refining concepts, there is no formal inheritance relation between concepts as there's for type classes, right? one of them is more specialized than the other, but there's no difference if the definition of equation of equal, was repeated inside ORD rather than defining ORD through equal. So I think this is just to confirm that there's no inheritance relationship.
There's no inheritance in a relationship. No, this is Haskell's type class special in this regard, and they work in a relatively different way. In Haskell, one type has to implement a concept. In C++, you check a concept. This is more like kind of a predicate.
All right. Then would you go back to the get smaller function that you showed and applied to different types?
Get smaller, was it
Get smaller. So you use this for integers.
Wait, other direction. This was with an unordered set. Yeah, here we are.
Correct. So the question is, what if A and B were types that individually satisfied ORD, but still there was no operator less than that compared an object of type A with an object of type B?
Once more, they support the concept ordering, but
correct, because get smaller has type ORD. B could be different types. So what if there is two types of type?
I see what you mean. So they could be different. They could be a string and could be an int.
Correct.
Of course, this would fail. This would fail inside. This could not work. But this would fail inside. But maybe then I define, in this case, I defined a function template, which makes not so much sense. This is a different question. Yeah, this would fail such as templates would fail. The classical template would fail. It's just a wrong template instantiation.
All right. And then there is one question that is repeated several times in different versions. I picked the first one. So you mentioned a couple of times that people should not write their own concepts.
Yep.
So was that argument limited to concepts already implemented in the standard library, or generally?
So sorry, what the question was, of course, you should not reinvent the wheel, to put it short. And the question was?
The question is the comment "don't write your own concepts" limited to the standard library things, or do you mean this in general?
You as a user, I mean it in general. First, you should look inside the standard if this concept is available, and if so, you are fine. And second, you should think what a concept is, to which I will come back a little bit later. You should not define the concept which is called has function ABC. This makes no sense. You should define concepts with which models ideas, general ideas, such what is a number, what is an integral, what is regular. This is a point to which I will come back later, because defining concept is more than just expressing requirements. It's about modeling ideas or modeling concepts. I know it sounds strange, but it's more than that. It's semantic. It's not only syntax.
All right. And then somebody is basically adding to the first question, is there an exception to the rule? So when should we write our own concepts?
This is a rhetorical question.
Okay.
There's always an exception to the rule. What should I say?
That's true.
Okay, sorry. I will not answer this question.
Last question.
Yeah.
Concepts or templates, can you use partial or full specialization on them?
Should be possible. I never tried it out, but it should be possible. I don't assume that here's some. So you want to partially specialize on partially or fully specialize on a concept. I see no reason why not, to be honest. I never tried it out. If not, I have to explain in my seminars, it works in general, but not here, which I don't like.
All right, that's the questions.
Okay. Then a short summary. What I talked about. then I will come to the final question or answer to the question. Okay, I talked a little bit about motivation, about this two wrong ways from my perspective: function which only work on one argument, function which work on all arguments. Both are wrong ways to solve a problem. I talked a little bit about the long history, in particular about the kind of similarity to Haskell type classes. Then I showed you that you can apply them in many, many different situations. In the placeholder syntax, I referred to this unification of auto and concepts, meaning that we now have placeholders and we have them in a constrained version, which are concepts, and in an unconstrained version, which is auto. Then I talked a little bit about syntactic sugar, which is, from my perspective, totally important. I showed you how easy is it to define a function template using a constraint or using an unconstrained placeholder. And at the end, I did something which I should not do. I defined concepts, but only to show you that under the hood, it often boils down to a combination of existing concepts or type traits from the type traits library, which we have since C++11. Now to the key question, and I was curious but you will hear it. Okay, are concepts evolution or a revolution? Honestly, you can argue for evolution or for revolution. What speaks for evolution? Of course, we have since C++11 unconstrained placeholders. Now we have constrained placeholders. It's a kind of an evolution. Of course, since C++14, we can use generic lambdas. And the point is that I can use auto instead of a concrete type. This is more an evolution. But now to the revolution part. Okay. Template requirements can now verified by the compiler. The compiler can check if a template parameter satisfies the requirement. If not, you will get an unreadable error message. What also speaks for the revolution from my perspective is that it's now quite easy to define or declare a template. And now to my main point for the revolution. You see that I'm more on the revolution side. Concepts define semantic categories and not syntactic requirements. I want to say a few words to this statement. What is a syntactic requirement? A syntactic requirement would be a concept which is called has function or has smaller operator. This would be a concept which just checks if the function, if the type has a small operator. This is a bad concept. This is only a syntactic requirement. You want to think in higher categories, such as equal, ordering. And this is the first time we think in this, I call it higher categories, sorry for the word. We could also call it, sorry for this strange term, Platonic ideas. What is a number? What means comparable? What means callable? What means? We now talk about semantic categories, about things we model and building a higher abstraction, modeling also in a kind of a mathematical sense. And this is something totally new for me. And this is the stuff which I like most, because we can now quite easily reason about our programs and we say, hey, this function takes all which behaves such as an int. This was it. Or just to put it other way, sorry, behaves just such as a number, whatever number means. Okay, this was evolution, revolution. I will come back to this slide in a few seconds, but let me first skip one slide further. if you are curious about this stuff and you want to learn German, you can read the stuff here. If you don't want to learn German, then you can read 50 to 20 posts on this on my blog about concepts. Okay, now I'm done with my presentation, and I'm not sure if you have additional remarks or questions. Maybe you have a different opinion to the evolution versus revolution statement I made. Any questions so far, Klaus?
No new questions so far. Oh, okay. Question. Imagine a world with only constrained placeholders. Okay, I don't know if this is a question
or statement.
or a statement, yeah.
I think before I come to this question, this is a new feature. This is a powerful feature, and this will change the way we think about generic code. Point. And we have to learn how to use this feature, and this is a learning process. So I'm curious how this process will evolve. But yeah, this is my answer to this maybe question. Okay, now a real question. What is the question, Klaus?
So, well, imagine a world with only constrained placeholders. Would that be a world you would want to be in? That's the question.
This is the same question such as before.
Yeah.
I don't know it, to be honest.
Okay.
I'm a big fan of it, but you should never say always. You should always never say always. Is it a? I don't know.
Right.
It's terrible.
But there's no further questions.
Okay.
Okay, now is a couple of thank yous.
Okay, I'm fine. I'm happy about. I don't know how many participants we had. I'm totally curious about what we did today, and I hope this experiment will work out in the longer run, because we should make these experiments more often in the near future, or we are forced to do it.
All right. Thank you very much, Rainer, for your time and sharing your experiences. And thank you for joining this little experiment of ours. I hope it was great. I hope it worked out for you. Please leave a couple of comments about your experience. So did the sound work well? Did the slides, so the visual work well? What do you think we can improve, etc.?
Okay.
Thank you very much. And I hope we can continue this experiment in other virtual meetups.
Maybe it will not be, this was the first experiment. Next time it will not be an experiment anymore.
All right. Thank you.
Okay. Goodbye to all of you.